for the question 1, where find dy over dx if y is equal to ln to the power of 2x plus e to the power of 3x. To differentiate these functions, I will use the change rules consist of several layers. It will become like this: y square bracket ln x plus e to the power of 3x to the power of 2. First, I differentiate the outer functions. D over dx u to the power of 2 is equal to 2u. This is because I let the power of 2 in front of the u. This equation will change to dy over dx is equals to 2 ln bracket x plus e to the power of 3x d over dx square bracket x plus e to the power of x. Let's move to the step 2. In this, here I use the formula d over dx ln u equals to 1 over u du over dx. Here, u equals x plus e to the power of 3x. It will become to u equals to x plus e to the power of 3x. Therefore, d over dx square bracket and x plus e 3x bracket is equals to 1 over x plus e 3x d over dx x plus e to the power of 3x. Now, on the step 3, we must differentiate the x plus e to the power of 3x. We differentiate the x first, where d over dx x is equals to 1. But for e to the power of 3x, we use the chain rule, where d over dx e to the power of 3x is equals to 3e to the power of 3x. So, the answer for this step is d over dx. Just rewrite this: x plus e 3x, and the answer is 1 plus 3e to the power of 3x. So the last step is just substitute the result back into the chain rule expressions, where the dy over dx is equals to 2 ln x plus e to the power of 3x 1 plus 3e 3x divided by x plus e 3 to the power of 3x. We just divide these questions, so we will get the answer dy over dx equals to 2 ln x plus e 3x 1 plus 3e to the power of 3x divided by x plus e 3x. So this is the answer for question 1. Now let's move to the next questions.
Assalamualaikum and hello everyone. Today I will be sharing how I solve question 2 using implicit differentiation. Basically, because x and y are completely tangled up together here, I can't just separate them easily. So the plan is to just differentiate every single term right where it is, moving from the left to the right. So instead of trying to do everything at once and making a mess, I decided to break down the two trickiest parts at the very top first. For this natural log term on the left, since there is a function inside another one, I had to use the chain rule. I basically differentiated the outside log first, which gave me 1 over the inside expressions, and then multiplied it by the derivative of what's inside. It cleans up these fractions right here. And then for the right side, there's a fraction, so I use the quotient rule. Applying that formula give me 2 over brackets x plus 1 bracket power of 2, which is also just a quick reminder for the plus 3y term. Whenever I differentiate a term with a y in it, I always have to attach a dy per dx next to it, so that's why it becomes plus 3 dy per dx. So moving on to the middle, once I got those separated parts done, I merged them back into the main equation. If you're wondering where the middle piece is, the 2xy dy per dx plus y square came from the xy square term in the original question. Since x and y square are multiplying each other, I had to use the product rule to expand it. So row 3 is just the entire differentiated line from left to right. From here on out, the rest of the steps are just normal algebra to get dy over dx by itself. So I added these speech bubbles on the side to make it easier to track. So in the first bubble, I group all the dy and dx terms together on the left sides and shifted all the regular terms over to the right side. Just remember that signs flip when they cross the equal sign, so the positive 3 dy per dx became negative. And for the next row, since both terms on the left side have a dy per dx attached to them, I just factor it out. I pulled it to the front and left the remaining 2xy minus 3 inside the brackets. And finally, to get the dy per dx completely isolated, I just divided the whole right side by the bracketed group. That brings me to the final big fraction answer at the very bottom. So yeah, that's how the whole step-by-step solution were made by me. That's all for now. Thank you.
Question 3. I will use differentials to estimate the value of square root 15.8 minus 2 over the fourth root of 15.8. So first, I define the function and write it using indexes so that it is easier to differentiate. Second, I use the power rule to find the derivative of the function. And third, since 15.8 is close to 16, I choose 16 as my approximation point. The change in x is negative 0.2. For the fourth step, I apply the linear approximation formula, which states that f of x plus delta x is approximately equal to f of x plus f prime of x times delta x. For the fifth step, I substitute 16 into both the original function and its derivative. For the sixth step, I simplify the values, which f of 16 equals 3 and f prime of 16 equals 9 over 64. And for the seventh step, I calculate the approximation, which are 3 minus 0.0281.
For question 4.1, I will explain differentiation in both its definition and concept. Differentiation is a mathematical process used to find the derivative of a function, measuring how quickly a variable changes with respect to another variable. Conceptually, differentiation is to determine the rate of change at a specific point. It also helps us find the slope of a curve and identify maximum or minimum values in mathematical applications and even real-world problems. Moving on, for question 4b, one practical application of differentiation can be found in business profit analysis. Businesses often use differentiation to determine the level of product that will generate the highest profit. For example, Suppose a company's profit function is given by P of x equals negative x squared plus 100x minus 1000, where P of x represents the profit and x represents the number of units sold. To find the maximum profit, we first differentiate the profit function. The derivative of P of x is P prime of x equals negative 2x plus 100. Next, we set the derivative equaling to 0. So we get negative 2x plus 100 equals to 0. Solving this equation gives us x equals 50. This means the company will achieve its maximum profit when it produces and sells 50 units. These examples shows how differentiation helps business make better decisions by identifying the optimal production level. Instead of relying on trial and error, companies can use calculus to maximize profit and improve efficiency.
So let's look at a critical reflection on why we actually learn differentiation. At its core, differentiation is simply the mathematical study of how things change. We learn this concept because the real world is dynamic and constantly shifting. In any professional field, relying on simple averages just isn't enough to manage complex operations. Differentiation gives us a precise tool to understand exactly how a system is behaving at any given moment. So first, let's talk about how differentiation helps us analyze systems. It allows us to measure the direct impact of our choices by showing exactly how a change in one variable affects another. Instead of guessing, it helps us to track real-time shifts so we can see how adjusting our inputs like time, resources, or effort will change the final output. But the real value of calculus comes down to optimization, which means making a system run as efficiently and productively as possible. We do this by finding the system's turning points, by calculating the derivative and setting it to 0, written as f prime x equals to 0, so we can locate the exact high or low points of a function. This mathematical process tells us the precise conditions we need to maximize desirable results, like speed or efficiency, while minimizing negative factors like waste, energy loss, or risk.